Alright, so I'm back again and I want to do a quick video about how to actually find the values for our transistor LED circuit. So how do we turn that circuit on? Remember, if we recall, that we need to bias a transistor to be able to turn the LED on. How do we find those values? Well, we do that using these two equations. So the first one we're going to use is the equation for the LED, and the next one we're going to use is the equation for the resistor at the base. Okay, how do we facilitate using these formulas? Well, first we have to write down our knowns. If we remember what our knowns were, we had a supply voltage, which is usually denoted as VCC. Our supply voltage is 5 volts. The LED, a typical LED, will run at 2 volts at 20 milliamps. Okay, another typical transistor, which is denoted as Q1, will run at 0.7 volts at 1 milliamp. That's our bias voltage. Okay, this is our bias. So we want to find the values that will hit those target points within that circuit. If we recall, again, our circuit looks something like this, and we're going to go actually on the computer website, every circuit, and we're going to look at how to do this. Okay, we're going to look at a simulation on every circuit on how to actually get this LED to turn on. So this is our circuit, this is our 5 volts here, this is our resistor. We want to know what our resistor value is here, and then we want to know what resistor value actually we need here as well to bias this base so this junction will turn on. Okay, so let's walk through some of the values here that we have in these equations. So for our LED, we have Vs, which is the supply voltage, minus the voltage that the LED needs, minus the current that the LED needs. Okay, I should put that there as well. Which is going to be, the supply voltage is 5, the voltage for the operating LED is going to be 2, and then the current is 20 milliamps. 20 milliamps, if we move that over and convert it to amps, it's going to be 0.02 amps. Okay, and then I'll just get my calculator real quick. 5 minus 2 over 0.02, and we have 150. Okay, so 150 ohms. 150 ohms right here. That's going to be our answer. So that is what we need here at R1 as our current limiting resistor. Now, what do we need for our RB, for our bias resistor? For our bias resistor, we're going to use the value of the voltage after R1 minus VBE, which is the voltage at the base emitter junction, which is our voltage of interest here. When we talk about the bias voltage, we're really talking about the voltage between these two junctions, between the base junction and the emitter junction. Okay, as I talked about in my last video, the transistor is made up between these relationships between these junctions, and each junction is going to have a certain voltage. We call that the bias voltage of the junction. What we're wanting to do in this case is we're wanting to supply the voltage at a certain point at the base and emitter junction so that the energy up here will be able to flow through here and then come in here and then go back to the battery and come up here and just keep completing the cycle, right? We want this to complete the cycle. Without this thing being biased, it cannot complete the cycle. Now this VBE, all that is going to be all over the base current. Now again, these are just generic nominal values that are very typical of transistors, of basic general purpose transistors. So this is going to be 1 milliamp, which is going to be 0.001 amps. Okay, actually I'll put that in the next equation, sorry. I'm going to put that in the next one here. So this is going to be IB, which is going to be our base current. So these values, now for VR1, we're going to use the voltage after. VR1 is right here. It's the voltage after this resistor, which is going to be less than this, right? Because it has this LED taking up the voltage. So the voltage VR1 is basically equal to VCC minus V LED, which is just 5 minus 2 gives us 3 volts. So we're going to use 3 volts there minus VBE, which we know our bias voltage, that magical number 0.7. Okay, 0.7 volts, and then our current 0.001, which is our base current. So this will tell us what resistor we need to turn this thing on. 3 minus 0.7 over 0.001. That gives us 2,300 or 2.3K ohm resistor. Okay, so now we have that value. So now I'm going to switch over to every circuit, and we're going to simulate this thing to show you how this actually works. Alright, so this is every circuit. If you haven't used it before, it's a great platform to learn electronics on. You know, in my day when I was learning, it wasn't a thing, but for people that are new to it, it's a great platform, but just because you can see how things work, you can, what this is showing us is basically it shows you the electron flow of your circuits, okay, when they're operating and when they're not. All right, so here I have the circuit laid out, but it's not turning on. As you can see, we have electron flow, because this kind of illustrates what I was talking about earlier, where there's presence. The only discrepancy here is that since this leg of the LED is attached, this voltage would be there. There would be these electrons. They would be there. They just want to go to the other side. They wouldn't go anywhere else, but they would be in that leg. Okay, just to note that the electrons, the voltage would be there, but it wouldn't pass through the actual light emitting diode. So as you can see here, we have the 5 volt supply. We have our 150 ohm resistor. Then we have our R2, which is our bias resistor. It's not the correct value, and that's why you see that the voltage is just going right through, and it's not turning on the LED. The voltage is just going right through here, going back into this circuit here. Now let's see if we can actually turn this LED on. So I'm going to get my pointer, and then I'm going to click on this. If we click on this and press the tool function, then we can change the resistance. So I'm going to change the resistance. Is now we can see now we're starting to get some current flow here. And what this is doing, as you can see here, is this is activating now the current flow between the base and collector junction as well. Okay, so now we're going to have some current flow that starts to generate between the collector and the emitter here. If we get closer to our value, which was, I believe, yep, 2,000.3, so 2.3K resistor, now we can see that the thing perfectly flows, but most of it going through the collector and emitter junction. So this is one of the reasons why transistors sometimes can be looked at, some people like to look at it as a valve, right? Because again, I'll illustrate this. If we throw this resistor, this voltage, actually I put it, not the voltage, but the resistance, if I put it really high, you can see that that limits the flow. But going back, this will demonstrate it better. If I go really low, like I had it before, you can see that it's not allowing the junction between the collector and the emitter to conduct. Okay, energy is just passing through it on the low side, let's say, but not on the high side. We can look at it that way. It's not allowing the collector emitter junction to conduct, but if we put in the value that we calculated thereabouts, then we see that it has the bias voltage. The bias voltage is reading here a little bit higher than what we desired. Electronics are always going to be, and I think this is why every circuit does this, it seems to mimic the kind of tolerances that we actually see in the real world, meaning that when we calculate all these things, we're looking at perfect ideal components, like ideal capacitors, ideal resistors, ideal transistors. Our numbers might be off a little bit. Like you see this 19.1 milliamps. You see we have 2 volts there. We have 0.8 volts instead of 0.7. All of that has to do with the imperfections with the materials that seem to be built into this program, which I think is actually nice, because in the real world, again, that's what happens. That's something I also like to stress to people that are getting involved in electronics, is sometimes I think when we want to learn it, we want to be very concrete, but you have to realize that there's actually there's a larger window of operation than you might think. You know, most of what we do when we're trying to perfect some kind of product or some kind of circuit is making it conducive to human operation and human interface, right? And sometimes, what does that mean? That means like mitigating noise, it means stability, it means consistency, it means being durable, and all those kinds of things. But as far as, you know, the specific numbers that we calculate, and let's say if it's off by 0.1, does that mean the circuit doesn't work? No, that doesn't mean the circuit. It could have an operation window of plus or minus 5 volts, plus or minus 20 volts, you know, plus or minus 100 volts sometimes, you know, depending on what you're looking for, right? So it's not always as precise as you might think, but doing these calculations, running it through simulator here, we can kind of see how things behave. It gives us a good idea of how to wire up our circuit. If we want to put this on a breadboard, we know exactly what resistor to use, in particular for the current limiting resistor on this LED, because if we use a resistor that's too small, then that LED is going to suck up a bunch of power and it's just going to burn out. Okay. So I hope you guys enjoyed that. That's how we find the values for our bias voltage and our current limiting resistor.